Hi, Assalamualaikum. My name is Muhammad Hafizi bin Abdul Manan and my teammate is Dr. Najidah Hambali and Dr. Nurul Nadia Muhammad. We are from School of Electrical Engineering, College of Engineering, University Technology Mara, Shah Alam, Selangor, Malaysia. And the title of our project is Nonlinear Modeling and Fuzzy Control of Steam Temperature for Distillation Column Pilot Plant. Okay, this is the outline of my video presentation. First, we have introduction that consists of research background, problem statement, and research objective. Second is methodology, consists of flowchart of the project, steam distillation pilot plant (SDPP), MPRS and PR-based input signal, system identification, open loop test which is two-point method, Ziegler-Nickel PID tuning method, and fuzzy logic control. Third is result and discussion. We have model estimation and validation, Ziegler-Nickel PID tuning table, and comparison Ziegler-Nickel PID and fuzzy logic control. And lastly, we have the conclusion to conclude all the findings of the project. Research background. First is about distillation column. Distillation is a process used to separate a mixture of two or more components into its reagent state by heating the mixture to a temperature between their respective boiling point. Distillation becomes an important separation method and widely used in industrial processes such as chemical and petroleum. And distillation column is well known for its nonlinear behavior. There are two types of model in distillation column, which are linear and nonlinear model. The linear model, such as autoregressive with exogenous input ARX and autoregressive moving average with exogenous input Rmax, model has been used in distillation pilot plant. But unfortunately, the linear model has some limitation due to its approximation that valid for specific input range and demonstrate low accuracy and fit compared to nonlinear model. And for nonlinear modeling autoregressive with exogenous input NAREX was proposed for the steam distillation column due to good performance for the distillation process compared to linear model. Several research employ NAREX to describe complicated nonlinear system with a high degree of accuracy and small margin of error. Nonlinear modeling has been demonstrated through the use of MPRS perturbation input signal in comparison to PRBS and lead to a better solution for identifying nonlinear system. For problem statement, there is a limitation in the study of implementation various input signal in distillation column for nonlinear modeling. In addition, linear approach in nonlinear system and control technique demonstrate lower accuracy and poor fitting than compared to the implementation of nonlinear model. For controlling method, conventional PID control has difficulties to achieve a better control performance for steam temperatures. Then, the main objective of this project is to model and control the SDPP steam temperature using NAREX model and fuzzy controller. And other objective is to estimate the nonlinear model of steam temperature using NAREX through PRBS and MPRS signal, and to design the fuzzy logic and PID controller based on estimated nonlinear model. And lastly, to analyze the performance of PID control and fuzzy control through PRBS and MPRS perturbation input signal. As you can see, this is the flow of the project that consists of SDPP setup, data collection, model structure selection, model estimation, model validation, fuzzy and PID control, and lastly, performance analysis. Okay, now this is the overview of the experimental setup for the project. In this SDPP, the water with a capacity of 12 liters is heated by an immersion heater in the distillation column. This SDPP uses a coil type heater to heat the water and produce steam. Two resistive temperature detectors, which is RTD, are mounted at high level and low level of distillation column. This RTD will produce an output in terms of voltage corresponding to the change of temperature. Lastly, a signal modulator with a 1.5 kilowatt 240 volt and 50 Hz power. This is the perturbation input signal used to carry out the process of the project. PRBS and MPRS input signal will be used for model estimation and validation to select the best transfer function to represent the plan for controlling pipe. Based on the perturbation input signal on the previous slide, model validation and estimation for PRBS and MPRS perturbation input signal were implemented using system identification in MATLAB. Various number of terms has been used to identify the best model output for the transfer function. The selection of the transfer function was based on high percentage of fitness and low value of mean square error MSE and final prediction error FPE. The accepted transfer function is being used to develop the controller for steam temperature. Okay, next part in methodology is open loop test. Figure 3 shows the SDPP temperature output for PRBS perturbation input signal. With this output response, second method of FOPDT, which is two-point method, was implemented in this project to find the parameter values such as gain, time constant, and time delay. These parameter values is needed in order to develop the PID control using Ziegler-Nicker tuning method. The formula presented in this slide is used to obtain the parameter for PID tuning. In this section of methodology, the value of proportional gain Kp, integral time Ti, and derivative time constant Td for MPRS and PRBS input signal are shown in table 2. The PID control is developed using Ziegler-Nicker tuning method, and parameter of Kp, Ti, and Td are calculated based on formula in table 1. Then, figure 5 shows the simulating block diagram that used to execute the signal using PID and fuzzy controller. Okay, the last part of methodology is designing the fuzzy logic control. To control the steam temperature, 2 input and 1 output was designed that consists of 7 linguistic variables, which are large negative Ln, medium negative Mn, small negative Sn, 0 Ze, small positive Sp, medium positive Mp, and large positive Lp. Trapezoidal and triangular shape of the membership function was used on this project. This shape has been selected because of the previous literature that state that this type of shape is suitable and efficient to control the steam temperature. And lastly, the output rule for fuzzy controller was mapping based on table 3. Since the input has 7 linguistic variables, it will produce 49 fuzzy metric rules. Next section of this slide presentation is result and discussion. For result and discussion, 2 tables of model estimation and validation for PRBS and MPRS input signal has been presented in table 4 and 5. For number of terms is being used to identify the best nonlinear model. Based on the result in table 4 and 5, the best nonlinear model for PRBS and MPRS input signal was chosen based on the highest percentage of fitness, low value of MSE and FPE. The results show that the PRBS input signal achieved highest fitness and low value of FPE and MSE with 1 number of terms, while MPRS signal required 3 number of terms to achieve best result for fitness, FPE, and MSE. In this slide, the control performance for PID and fuzzy has been compared. The comparison of this control method is based on value of rise time, peak time, settling time, and percentage of overshoot. Figure 8 shows the simulation result of PID controller, while Figure 9 shows the simulation result of PID and fuzzy controller. What can be concluded from the table and figure shown on the slide? The value of rise time, peak time, settling time, and overshoot for PID Ziegler-Nicker using PRBS input signal demonstrated slower response compared to PID Ziegler-Nicker with MPRS signal. Then, for fuzzy controller, MPRS input signal presented fast response compared to fuzzy with PRBS signal. As a conclusion, fuzzy controller for controlling steam temperature in nonlinear modeling has been presented. System identification for PRBS and MPRS input signal has been conducted for model estimation and validation. Then, two-point method of FOPDT was used to calculate the value of gain, time constant, and time delay. Based on the simulation result, it can be concluded that fuzzy controller with MPRS perturbation input signal demonstrate fast response in rush time, peak time, settling time, and percentage of overshoot compared to the Ziegler-Nickel tuning method and fuzzy controller with PRBS input signal. Okay, that's the end of my video presentation. I would like to thanks to panel for lending some time to see my video presentation. And that's all from me. Thank you and Assalamualaikum.